In chemistry, they feel there's more than 20 million known compounds, and that's a huge number. But most of them are based, of course, on carbon and oxygen and nitrogen and hydrogen, things like that, the organic compounds. So even though I love my metals, in the last chapter we looked at, chapter 19, most of the chemicals, of course, are based on organic chemistry. And carbon is amazing, all right? Carbon is really cool in the kind of things it does. And it's not just carbon, it's hydrogen and oxygen and stuff like that. But if you look at the 4 different structures we're seeing there, this is just some representations of what carbon can do. And some of them we've seen before in similar circumstances, some of them we have not. Carbon is amazingly versatile, and we'll see how carbon can bond to itself in a variety of ways and make a variety of different compounds that probably are new to you, or maybe you haven't expected before. So in organic chemistry, the year-long class, there's basically 2 parts to it. And the first is nomenclature, being able to name the molecules correctly. And that's what we're going to focus on this section, all right, in this little section of Chem 223. We won't be able to do justice to, of course, the complete year, and we're not going to look at all the details of nomenclature either. But we'll give a good examples and see kind of how this rolls together so that if and when you take the actual class, you'll be good to go. But the majority of organic chemistry is on reactivity, and reactivity, of course, is how you make the molecules that you're talking about, and also what you do with the molecules once you've made them. And it's a huge area. I'm going to give you a couple of examples just for fun, but again, I won't quiz or ask you any questions on anything to do with reactivity. We're going to focus on nomenclature. So anyway, it's a cool chapter. Honestly, organic chemistry is where I really learned to love chemistry. I mean, I'd always liked it before, but in organic chemistry, wow, it hit hard. So even though my weird start to it that I want to have you avoid at all possible, I really did learn to love chemistry by looking at organic chemistry. So let's check this out, see what it has to offer, and see if I can entice you further into the world of chemistry. From the Lewis structures and Vesper geometry studies we did back in Chemistry 221, carbon can only make 4 bonds, and that's a hard limit. All right, carbon cannot make 5 bonds, stuff like that. Now, sometimes it can do strange things and make different ones, but it's 4 bonds is kind of the rule. Now, on the right-hand side are different ways to write carbon. Now, remember that the actual carbons are usually going to be tetrahedral, which is 109 degrees. So sometimes, like in the top there, I will write just 4 carbons in a row. But really, in the real world, those carbons with single bonds would all be tetrahedral, and they would be about 109 degrees apart from each other. And likewise, if I draw the next one with 3 carbons in a line and 1 carbon down, that would be something like the one below. And then you can have different combinations like this one and this one, all these kind of things. So despite the limitations of our drawings, you have to remember in the back of your mind, this is still 109 degrees, tetrahedral, sp3 hybridized, if you remember all those terms from Chem 221, no worries. So these skeleton drawings are very common, or line drawings, all right? They're just showing the carbon atoms. They don't necessarily show all the other atoms. Now let's assume that those 4 atoms there on the top level, they're surrounded with hydrogen, no problem. So the actual structural formula would look like that, and that shows all the hydrogens and stuff. However, notice the carbons are all in a row. But maybe you're using Microsoft Word and you can't make fancy lines up and down, then you might want to make a structure like that, sometimes called a condensed structure. However, in organic chemistry, hydrogen is so prevalent, often the hydrogens are completely omitted. So this next one right there is a true line structure. It's called a carbon skeleton formula, and it only shows the carbons. It doesn't show the hydrogens. And you, as the hip chemist, need to know that every one of those vertices is a carbon, and carbon has to have 4 bonds. So if there's nothing else showing, then there's going to be bonds to hydrogen. So for example, on the very end, on the left-hand side, that little vertice, that would be a carbon. It would have another bond to the next vertice, to the next carbon, but that carbon with only 1 bond would have 3 hydrogens around it, etc., etc., etc. Now, ball and stick stick will show the tetrahedral nature of all the atoms really well. Space-filling models on the far right will show what the electrons are probably more like because they actually mesh together. They don't have nice little single bonds. Anyway, welcome to the world of organic chemistry. There's many different ways to show them. Now, those carbon skeleton formulas in the middle will be important. A lot of times this is how organic chemists write them. Hydrogen is just all over the place, so if you can ignore the hydrogen, it's easier. That's why those skeleton formulas will show up a lot. So kind of familiarize yourself with these. And by the way, you can have double bonds and you can have triple bonds, no problem. Notice in the skeleton formulas, the double bonds are kind of like straight across, triple bonds literally 180 degrees from each other. All the things we learned in the Lewis structures / Vesper area still applies. We're just thinking about organic chemicals now. So to build an organic chemical, you need to know about the alkyl groups. And alkyl groups are literally the building blocks of the organic molecules. And these names that the alkyl groups are going to be referred to are going to resonate with some of the families of organic chemicals we'll look at here in a little bit. All right, so the alkyl groups aren't compounds themselves, but you can combine an alkyl group with hydrogen, chlorine, another alkyl group, whatever, to make a molecule. The simplest of the alkyl groups is called methyl. Methyl has a single carbon that's in a tetrahedral environment. It's sp3. So you can see there from the methyl group that carbon has 3 hydrogens, but carbon needs to have 4 bonds. So there's like one spot on the carbon left over to bond to something else. So the methyl group is not an organic chemical, but it's a building block of the other things we're going to see. So while methyl is associated with 1 carbon, ethyl is associated with 2 carbons. So if you put another tetrahedral carbon on that CH3, now the carbon on the far left has 3 hydrogens and a bond to carbon. But the bond on the right now, which has a bond to carbon by the way, has 2 hydrogens and 1 more spot. So it has another place that it can make a connection to. So again, ethyl and methyl, they are not compounds, but they're the building blocks of compounds we're going to see. So 1 carbon is methyl, 2 carbons is ethyl, 3 carbons in a row becomes propyl. So you can see there's 3 carbons in a row like that. No problem. You're just adding another tetrahedral sp3 on the end. And you can have butyl, and you can have all kinds of them. So methyl is 1, ethyl is 2, propyl is 3, butyl is 4. Pentyl would be 5 carbons in a row, again all tetrahedral sp3. Hexyl would be 6, heptyl 7, octyl 8, etc., etc. And sometimes people will use a capital R to represent a generic alkyl group. We'll talk about this more in a little bit. And again, none of these alkyl groups are compounds unto themselves, but they're the building blocks of it. So we'll see how they can be built up. Now down here in the bottom, I have a link to the Organic Chemistry Nomenclature Guide, which is in your companion and online. It has a lot of these families as well as the alkyl groups, and you can see how the alkyl groups will be helpful. So I encourage you to check that out in this section. Alkyl groups are not compounds, they are sp3 hybridized carbons, and they're missing 1 component. So again, you're not going to have a compound out of them, but you will be able to build them to make cool compounds. A hydrocarbon is a compound that has carbon and hydrogen in it. And sometimes hydrocarbons will have oxygen, but officially, of course, a hydrocarbon is just hydrogen and carbon. And so what we're going to do now is look at the simplest of the organic families, and it's in a family called the alkane. So an alkane is just an organic compound which has an alkyl group with a hydrogen. So all of those alkyl groups were missing something. So like on the upper left-hand side right there, that's the methyl group. It's a CH3. Carbon likes to have 4 bonds, so there's 1 part missing. Well, if we would plug that missing part with a hydrogen, that makes an alkane. All right, so an alkane is just an alkyl group with a hydrogen. If you can use any of the alkyl groups that we talked about. So any alkyl group R can be combined with hydrogen to make an alkane, RH. CH3 is methyl. If you add a hydrogen to it, it makes an alkane. And if you want to know how to name it, you take the YL off the alkyl, so methyl becomes meth. Not that kind of meth, trust me. Anyway, meth, and then you add ANE to it, methane. So CH4 is methane. It's a methyl group plus an H. all of the alkyl groups have a formula that they follow. For every n carbons, there are 2 n plus 2 hydrogens. So for methane with 1 carbon, n is 1. And so 2 times 1 plus 2 is 4. That's where CH4 comes from. Methane is CH4. This is the simplest of the alkanes. It's a great example, though, of how you can take an alkyl group, a methyl, and put a hydrogen on the end of it. If you take an ethyl group, which has 1 more carbon than a methyl group, and you put a hydrogen on the end of it, the ethyl group becomes ethane. So notice we're just putting another hydrogen on the end of another alkyl group. That becomes CH3CH2 with an H on it, or CH3CH3, which is ethane. So ethane is the next part of this family of compounds. It's also an alkane. All the alkyl groups are tetrahedral, sp3 carbon, stuff like that, and just hydrogen on the end. So ethane has 2 carbons. Ethyl minus Yl plus ane becomes ethane. And if you follow the formula, there are 2 carbons in ethane. So N is 2. 2 times 2, 4 plus 2, 6 hydrogens. And that's what ethane has. Let's keep going. Propyl is the next group. If you add a hydrogen to it, it becomes propane. And propane has 3 carbons, so N would be 3 in the formula. 3 times 2, 6 plus 2, 8 hydrogens. Lo and behold, that's what you've got. Now, methane is the active ingredient in natural gas. So if you have a house that's heated by natural gas, you're using methane. In our labs, all of the gas outlets for Bunsen burners are essentially a methane source. Ethane isn't as much as abundant as methane, but it is around. It's part of the ingredients in natural gas as well. Propane is used for barbecues a lot. If you have a propane heater, you are using propane, which is kind of cool. When you get to 4 carbons, you get to the butyl group, and the butyl group plus a hydrogen will make butane. So butyl minus Yl becomes but plus ane, butane, no problem. 4 carbons in a row is great. However, chemists run into a problem when you get to butane because of the existence of isomers. Now, an isomer is when you have the same structure, same number of atoms, but you can orient the atoms in different configurations, and this begins to happen at butane. So check this out. You can have 4 carbons in a row, which would be this version right there. And you can see literally it's 1, 2, 3, 4. Now actually it's tetrahedral 109, but you get the idea. 4 carbons in a line, kind of. But you can also take one of the CH3s on the end there and put it on the middle carbon, and you'll flop the hydrogen back to the original position. And that's when you end up with this structure. So chemists have to be very, very careful at this point and name them appropriately because they are both C4H10. But N-butane and what's called 2-methylpropane are quite different. So notice how they name the one structure on the right. The longest chain, smallest number is something we're going to talk about. So if you count up the number of carbons like in a chain, in a row, that would be 3 carbons. And to count it up in a chain, you go 1, 2, 3, but you can't go backwards. And you can go 1, 2, 3 with a top, or 1, 2, 3, not include the left-hand side, whatever, but you're going to have 3 carbons. And there's 1 carbon that's not in that longest chain, and that's that one right there. So this would be a methylpropane compound. The longest chain would be 3 carbons, and if that was an alkane, it would be propane, but you have a methyl group off of it, so this would be methylpropane. That's off the 2nd carbon, so that's why it's a 2-methylpropane. We'll talk more here in a little bit about longest chain, smallest numbers, but that's what it's going to mean. We have to have a way to differentiate those kind of isomers from the regular ones. And notice on the left-hand side even there's an N in front of the name. N means the normal version. So N-butane would literally be 4 carbons in a row. 2-methylpropane is an isomer of butane, all right? But it's not N-butane, so oh joy. So here's a question you might see: which of the following could be an alkane? And to answer this question, we're going to go back to the formula for an alkane, CnH2n plus 2. So for every n carbons, you'll have 2n plus 2 hydrogens. So if you look at C2H4, N is 2 carbons. 2 times 2, 4, plus 2, you'd have to have 6 hydrogens for it to be an alkane. C2H4 has just 4, so that means that it is not an alkane. And the same thing for number 2. Notice there's a 2 hydrogen to 1 carbon ratio, just like on number 1. That's also not going to have enough hydrogens. If you had 5 carbons, you'd have to have 12 hydrogens for it to be an alkane. But on 3, N equals 14, 2 times 14, 28 plus 2, C14H30 could be an alkane. Absolutely. It's got the right ratio. That's kind of the idea here. Now, number 4 doesn't have even close to the ratio of hydrogen to carbon that we need. It's much less. And number 5 has an oxygen atom, and we haven't dealt with oxygen atoms yet. So the only one here which could be an alkane would be number 3. That's the only one that has the right ratio of carbon to hydrogen. You need more than 2 to 1. You need 2n plus 2 to 1, basically, in order to make that happen. And number 3 does, but 1, 2, and 4 don't have the ratio. Number 5 has oxygen, so that's totally something different too. Welcome to organic chemistry. This is an overview of the different structures we've seen so far for the simplest alkanes. So for N equals 1 carbon, we had CH4. That's methyl plus hydrogen methane, no problem. When you get to 2 carbons, then you have ethyl plus hydrogen ethane. Ethane is 2 carbons. And notice that this is the first one that you can draw a line structure on, because you have then a couple of pieces there. So you can see there's a line structure for ethane, but for methane, there was nothing. It would be like a dot, and that's usually not seen as cool. So methane doesn't get a structure. Darn it. But ethane on does, no problem. When you get to 3 carbons, it's propane. Propane has 3 carbons like in a row, so you're good to go. When you get to butane, then you get to 2 different isomers. C4H10, which has a straight chain structure, i.e. all the carbons in a row, that's officially called N-butane. And the one below it with the methyl group, CH3, sticking off the propane chain, that would be 2-methylpropane, or sometimes just methylpropane. All stuff you can do. Pentane, 5 carbons, you actually end up with 3 isomers. Now in the upper left-hand corner, you see N-pentane. That's the generic version, 5 carbons in a row. But if you take 1 carbon off, you can make 2-methylbutane, which is there on the right-hand side. Now, longest chain, we have 1, 2, 3, 4 carbons, and you can't get any longer than that. So if that was an alkane, that would be butane, and then we need the smallest number. Now notice the note there. If you count left to right, it kind of looks like this would be carbon 1, 2, 3, 4. It kind of looks like it would be a 3-methylbutane. But here's the thing about organic chemistry. You always have to check to make sure you have the smallest numbers possible. And just because in the English language we're used to reading left to right, it doesn't mean you can't check right to left. So let me use a different color. This would be carbon 1 on the right, 2, 3, 4. So this compound can also be called 2-methylbutane, and smallest number always wins over larger number. So the very best name here is 2-methylbutane. 2 is smaller than 3. Smallest number is fantastic. The last isomer in the lower left-hand corner there, the longest isomer is a 3-carbon chain. That would be a propane if it was just a regular alkane. But there are 2 methyl groups, both off the 2nd carbon. So it's a dimethyl because we have 2 methyl groups not in the chain, and they're both off the 2nd carbon. So 2,2-dimethylpropane would be the way to name that. And again, longest chain, 3 carbons in the middle. You count left to right and or right to left. Going to give you the same on this one. 2nd carbon has both of the methyl groups. Here's a methyl group. Here's a methyl group. 2 methyl groups means dimethyl. They're both off the 2nd carbon. 2, 2 to show where they are. 2,2-dimethylpropane.
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the second carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the third carbon position produces 3-methylpentane. Moving the methyl group to the fourth carbon position appears to make 4-methylpentane. But wait, rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the second carbon position produces 2,3-dimethylbutane. Moving the methyl group to the second carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the third carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
The more carbon atoms you have in your compound, the more isomers you're going to find. And isomers are important. You could tell they're from the boiling points that they're all over the place. That's because the polarity changes. And as polarity changes, they tend to stick or not stick to each other as well. It changes all the properties of the different molecules. And just realize it gets crazy. So butane had 2, pentane had 3, hexane has 5. You can see where it's going as you go up and up and up. So just kind of realize it. And that's why this longest chain, smallest number mantra is really important in organic chemistry, and we'll talk about it now a little bit. So let's say you wanted to name the compound in the upper left right there, all right, and it's got quite a few carbons. So what you would do first is you would circle the longest chain of carbon atoms. So if you think about this long enough, you can circle 6 carbon atoms, which is what the red box there represents. And if this was a regular alkane, 6 carbons would be hexane. But the methyl group, of course, is not in your longest chain. It wasn't part of what you circled. So the next thing you have to do is you have to figure out the smallest number for the methane. Now, you don't have to count top to bottom, left to right, right to left, whatever. And you probably should practice both ways. So as an example of that, let's say that we started with a carbon here on the right. I'll call it 1. Then the next one would be 2, 3, 4, 5. And then the last one there would be 6. So you could call this, because this methyl group is off my 5th carbon, you could call this a 5-methylhexane. But as you see correctly there, the better name for this is definitely, if you start counting at this carbon, 1, 2, kind of covered it up there, kind of sloppy, 3, 4, 5, 6, 2-methylhexane is a better name than 5-methylhexane. So you always want to use the smallest number possible. Longest chain, smallest number. I erased all my garbage there and stuff so you can see a little bit better. So what you want to do is you want to find the longest chain in the molecule, and I would circle everything until you get it. And again, 6 carbons would be better than 5 carbons. That's what longest chain means. And then you want to number the chain from the end nearest the first substituent. If you have questions, number it from both sides, so left to right and right to left, for example. And that's what's going to be important, because the substituent, like the methyl group in this case, you want it to have the smallest number. So like I showed you earlier, it could be a 5-methylhexane, but that's not very cool. All right, 2-methyl, a smaller number, is better than 5-methyl. So the best name for this compound is 2-methylhexane. Now, if you start talking to people and you said 5-methylhexane, they would understand you. There's no question. However, it's kind of like saying, I ain't knowing what you're doing. It's like kind of using like hick language. And I want you to be official chemists when you talk to other chemists. So that's why I really want to highlight longest chain, smallest number. And if you do that, you are good to go. Here's another example. Now this is a lot more kind of convoluted here, but again, longest chain, smallest number is what you want. So if you look at this structure long enough, you can see in the red box right there, you can get up to 7 carbons. And again, it's not necessarily going to be all in a straight line, but you can figure out what it's going to be, 7 carbons. Now, not connected to that to that red box line thing that's going on. You can see that there's a methyl group on the left, a methyl group kind of in the lower left, a methyl group in the lower right, and a CH2CH3 group, which is an ethyl group also. So we have to name those compounds. Now, since there are 3 methyl groups, we're going to call this a trimethyl system, and the ethyl will be by itself. So 7 carbons in a row is a heptane. Heptyl, it makes heptane as the name. Ethyl will come before methyl because alphabetical things are important. And we're going to have a trimethyl. But now we need the numbers. And this is where, again, I recommend that you number things from both sides. So using the correct methods there, you can see it's going to be 2, 4, 5 trimethyl and a 3 ethyl. But let's say again that you wanted to try it the other way, which I encourage. Well, you'd have 1, 2, 3, 4 would be the same, 5, 6, 7. So if you look at this long enough, you have methyl groups of the 3, the 4, and the 6. So you could have 3, 4, 6 trimethyl. The ethyl group would be off the 5. So you could have a 5 ethyl, 3, 4, 6 trimethyl, but you can see that all those numbers are essentially bigger than what you had before. So that's why counting in that direction doesn't make any sense. So again, this longest chain, smallest number is just something to get used to. We'll just kind of introduce it here. In organic chemistry, you'll look at this in a lot more detail. But it just helps chemists to understand the structures they're looking at, and you can then talk to each other about them and know what you're talking about, basically. So here's a question, a little simpler. It says, what's the name of this organic compound? So again, remember, longest chain, smallest number, all right? So looking at that molecule right there, what you want to do is figure out the longest number of carbon atoms. And one thing you could do is circle 3 of them. All right, that would be some kind of propane molecule like the last answer. But wow, that's not right, because if you look at this long enough, 1, 2, 3, 4, you can get 4 carbons circled. 4 carbons is a longer chain than 3 carbons, so we're going to stick to 4 carbons. That would be a butane if it was an alkane. Now we have 2 methyl groups that aren't in my circled blue line right there, so this will be a dimethyl butane. But what we also need now, of course, are the numbers. Now both of the methyl groups are off the same carbon, so it's going to be either answer B, 2,2-dimethyl butane, or C, 3,3-dimethyl butane. And if you count left to right, 1, 2, 3, 4, it kind of feels like it could be a 3,3-dimethyl butane. But remember, if you're just learning this especially, count both directions. So now on the top, I'm going to count right to left, and 1, 2, 3, 4, you can see I circled the 2. You could also call this 2,2-dimethyl butane. So when it comes to organic chemistry, longest chain, smallest number, and 2,2 is better than 3,3. So we would call this as chemists 2,2-dimethyl butane. Longest chain, butane, smallest number, 2,2, not 3,3. Good to go. Here's an example of taking a name and creating a structure. So let's figure out the structure for 2,2,4-trimethyl pentane, okay? And again, remember, longest chain, smallest number still exists, still is in effect. What I would do in a problem like this is start on the very end. I would start with the pentane, all right? So start on the very end. Pentane is a 5-carbon alkane, and let's just call them 1, 2, 3, 4, 5 like that, all right? You can count it right to left or right at this point. It doesn't really matter. Anyway, once the pentane is gone, then the first part says 2,2,4-trimethyl. So tri is 3. We have 3 methyls, and you can probably imagine those methyls are going to go at the second, and the 4th carbons. So here's like a structure of it. You can see on the second carbon there's 2 carbons. That would be the CH3 methyl groups. But there's also a CH3 off the fourth carbon. So this would be the backbone for this 2,2,4 trimethyl pentane compound. And then if you want, you can get fancy and make some line drawings, put in some H's, whatever you want to do. Honestly, the middle drawing is fine. The latter drawing there at the end is a little fancier, but it's all good. All right. Just remember that if you have a carbon, they have to have 4 bonds. And so 4 bonds, you'd fill them in with hydrogens. So here's a question that you can just try on your own. And if you don't want to, you don't have to. But anyway, it says to draw 2,3,4 trimethyl pentane. And if you want to pause it and stuff and try this on your own, that would be fantastic. I don't really care what answer you put down. But anyway, here's the punchline. Start at the end. Pentane. That's 1, 2, 3, 4, 5 carbons, just like before. All right. That would be the pentane backbone if it was an alkane. But you can probably see it's not just a pentane. We have a 2, 3, 4 trimethyl. So tri means 3 methyl groups. So if you count left to right or right to left, doesn't matter on this one. I'll count right, left to right. 1, 2, 3, 4, 5. What this means is off the second, the third, and the fourth carbons, you're going to have a CH3. So CH3 off the second carbon, CH3 off the third, and CH3 off the fourth, that's the trimethyl part of it. So this would be the backbone. Now, carbon always needs to have 4 bonds. So for example, this carbon on the end here has just the 1 bond to carbon. There would be 3 hydrogens on that. On the other hand, carbon number 2 right there has 1, 2, 3 bonds to other carbons. It would have only 1 hydrogen. So here's a fancier version of the drawing I just had. This would be 2, 3, 4 trimethyl pentane. And if you count the middle parts there, there's 5 carbons. You can see the CH3 on the left and the CH3 on the right, and the middle carbons are just points, like those vertices. And then off the second, third, and fourth carbons, there's a CH3 methyl group. That's the trimethyl part. Good to go. Nothing you can't handle. It gets kind of fun after a while, but anyway, fun in me. I don't know if that's the same definition as you have, but for me, it's kind of interesting. Anyway, okay, I think it's fun. I'll admit it. All right, on to the next problem.